Hello there. In this lesson, we're going to look at single and double displacement reactions. What do you mean by displacement? Well, displacement means it's going to remove one component from a compound and replace it with something else. And so you can kind of see a replacement going on here, where we start off with some copper metal, which you can see at the top there has that kind of brownish orange color. And there's a different metal in here. That's actually silver. And so one is displacing the other out of the compound which is in the solution over here. With double displacement, the situation happens twice, and you end up forming a whole new compound rather than just one element. So let's dig into it. So single displacement is where one element takes the place of another element in the compound. So one of them displaces one other one. You end up with the displaced element separate, and the other two ions will stick together. So an example here from the picture we looked at previously is copper metal here displacing the silver from a solution of silver chloride. So over here we had some silver chloride, and what happened is the copper bumped the silver out of the solution and it came out onto the surface of the copper there. So that's silver there down at the end. So you end up with the silver all by itself, and you end up with some copper chloride. It's actually copper 2 chloride. You can tell because of this blue color. That's something you'll learn at a later date. And this is aqueous in this case because you can see that it's in solution. So single displacement reactions follow a sort of hierarchy where only elements that are higher up on a given list called the activity series can displace those that are lower down. And so what you see here is that if you have some barium, it's higher up than the zinc, and it'll be able to displace the zinc and end up producing some barium chloride, probably in solution, and some zinc metal. But if you did the reverse, if you take the zinc and try to displace something above, that won't work. So going down works, and trying to displace upward will not work. Otherwise, the reaction just go round and round in circles, right? So there's an energy reason for all this happening, which you don't have to worry about in grade 10. But it means that the energy will push the reaction in one way and won't push it in the other way. And so it follows this neat pattern that we can keep track of using the activity series. So you'd say no reaction for the reverse. So it turns out nonmetals can also displace each other. The only ones we're going to look at are the halogens, which of course is group 17 here, just these top 4. And it works in the same way that an activity series does, where fluorine can displace everything. Chlorine can displace those below it, but not the fluorine, and so forth, right? So we got fluorine and chlorine here, means the fluorine can displace the chlorine, and you'll get a reaction, so you get some NaF in solution, and some Cl2 gas. They'll come bubbling out. For the one below, you see we got the chlorine and the bromine trying to displace it, and we'll have to say that there's going to be no reaction there because the bromine is lower down than the chlorine. So it's going to try to displace, and that won't work. Fluorine can go down, and that will work. So the second type of reaction is a double displacement, and it's very similar to the first one. It just happens twice. So where in the first one, A would displace C and C would end up all by itself, this one is going to go in both directions where C is also going to displace A. And you'll end up with new partners for both of the anions. So if we look at our example here, the one that makes this yellow solid, you're going to end up with the lead with the iodine, and you're going to end up with the potassium with the nitrate. Now you'd actually have to test to be able to tell which of the products is this yellow stuff. And so you don't have to worry about putting states in for these guys, but I can do it for you because I know what they are. So yeah, just do a double switcheroo, and you can end up with products for a double displacement reaction. Okay, so let's try a few of these double displacements and see if we can work out the products. The products you have to make sure have the right formula based on the charges. So we got sodium with a +1 here, carbonate with a -2, bromine with a -1, iron with a +2. And so if we do our switcheroo, it's going to be Na with the Br, and we're going to end up with Fe with the CO3, and looks like they're both even charged, and we'd only need a 2 there to balance out these 2 sodiums and 2 bromines. Now the next step, we got zinc, which has a +2 charge, nitrate, which has a -1, potassium, which is +1, phosphate, which is -3. So the potassium and the nitrate going together, that's no problem. They're 1 and 1. And then this zinc and the phosphate, that's a little more complicated. The zinc's going to get the 3, and the phosphate is going to get the 2. Now balancing this is a little trickier, right? We only have 1 phosphate on the left, and we have 2 on the right, so we're going to put a 2 in here. And that takes care of our phosphates. Then our zincs, we got 3 zincs on the right and only 1 on the left, so we're going to need a 3 there, and that takes care of the zincs. Now over here we have 3 times 2, that's 6 nitrates, and 2 times 3, that's 6 potassiums, so a 6 here should take care of the rest. The last one here, we have lithium with a +1, sulfate with a -2, aluminum with a +3, chlorine with a -1. So we're going to end up with lithium chloride, which is great because both of those are +1, -1. And then we have aluminum and sulfate, which is similar to the last one. We're going to have aluminum with the 2, and we're going to have the sulfate with the 3. And then the balance will also likely be similar. We got 2 aluminum, so we'll need 2 there. We got 3 sulfates, so we'll need 3 here. And that's going to end up with 6 lithiums, same balance as the one above. Okay, so to finish things off, I just want to remind you again about how you can work out the states of different substances. For elements, it's pretty easy because you can just base it on the color from the periodic table. There's calcium, it's black. That means it's a solid. There's bromine, it's blue. That means it's a liquid. There's argon there, it's red. That means it's a gas. And technetium over here is hollowed out, which means it's synthetic, which means you don't find it in nature. You can only make it in a nuclear reactor. Okay, now predicting the states of your compounds is a little more complicated. So there's a few basics I want to share with you. Hopefully that'll plant some seeds for you to understand states a little more going on. So the first one is like something that you can apply across the board. As long as you have a dry ionic compound, as long as there's no water around, it's going to be a solid. So dry sodium chloride, always going to be a nice solid crystal. Now, some ionic compounds can dissolve, and they get this AQ symbol, which stands for aqueous. And so sodium chloride is one of those, and so it would be an AQ for that one because it dissolves. Now, if you are in the lab and you see that something is dissolving, well, then you can use that AQ symbol as well, but I won't have you predict. Maybe in grade 11 we'll get to that. And then you're going to look at your molecules. Molecules have quite a variation in the states. They can come in all 3 states, but the general trend is that the bigger the molecule, the more solid it will be. So really, really tiny molecules like carbon dioxide are going to be gases. Medium-sized molecules like vinegar are going to be liquids, and large molecules like candle wax, those are going to be solids. So you can make an educated guess if you want to. I won't have any marks in my class associated with this, unless it's something that you've seen in front of you in the lab and have a frame of reference for. So let's finish by doing a few single and double displacement reactions together. This first one you can see has 2 compounds, so that makes a double displacement going to occur here. I like to put the charges on here just to help everybody when it comes to making your new compounds. And you can see that our calcium and our carbonate are going to go together nicely because they're +2 and -2, and then the sodium and the chlorine are going to go together because they are +1 and -1. And we can balance these out by adding 2 here. That'll take care of everything. Now for the next one here, we're going to look at magnesium and iron and nitrate. So magnesium, when it ionizes, is going to be +2, and nitrate is going to be -1. And this iron is just going to get displaced, so we don't have to worry about that one. So we're going to have iron all by itself as a solid, and you're going to end up with magnesium nitrate. And don't worry about the states right now. To double check that that's possible, you want to check on your activity series. There's magnesium, there's iron, which means that magnesium can displace the iron, and we're okay. The next one here, we got lead and zinc. Looking back at our list here, there's lead and there's zinc, and we're trying to go this way, which means it's not going to happen, and we'll have to say no reaction. This one that comes next here is double displacement because we have two compounds. We'll put in some charges, +1, -2, +2, and -1, which means we're going to end up with pretty much the same one as the first one here. You got nickel and carbonate, and we're going to end up with lithium and nitrate. Looks like we got 2 nitrates there, so we're going to need 2, and that should take care of all the balancing. The last one here is going to also be a displacement. The chlorine is going to try to displace that bromine. There's chlorine and there's bromine. We're going down, so check. That means we're going to end up with some aluminum with the chlorine, and we're going to end up with some bromine, which is part of Hofmickel. So to balance these out, we're going to need a 3 here, and a 2 here, and a 3 here, and a 2 here. And as far as states go, the elements we can include, we know that bromine is blue there, which means it's a liquid, and I won't have you predict your compounds just yet, but you can make some guesses if you wanted. There's some aqueous ones beforehand, and basically anything that dissolves you know would be an aqueous. So the one I would expect you would know would be sodium chloride because you've seen that before. All right, take care. We'll see you soon.